Okay. On last Thursday, we talked about frequency regulations, and we introduced some very basic concept of frequency deviations and the standards from the industry on what frequency is considered normal frequency, what is considered abnormal frequencies. Then, following that, we gradually developed the models for each component of the low frequency control until we came up with this the plot diagram, so we can derive a frequency transfer the transfer function in the frequency domain. So the entire loop has 4 blocks. So this one, the first one, is from a swing equation. This is what we know from the frequency equation. So that describes how the mechanical power and load change will cause the deviation of the frequency. And to change the mechanical power, we need to model a turbine. So here we just use the first order linear component to model the mechanical power change due to a valve opening change. And the valve opening change will be controlled by another component, which is a governor. So the governor will measure based on the feedback signal about the frequency deviation compared to the reference signal, and to decide whether we want to increase or decrease the valve opening. Remembering the centrifugal governors we show in last lecture, which is based on very simple and classical design, try to translate the signal of the changing of the speed by the distance between the 2 flying waves. And the flying wave will move the linkage of this mechanical system until influence the valve opening. For instance, if the speed is increasing, and this point will go down, and this point will go down, and so that will make more oil enter the tank and push the valve go up. Okay, and so that can sense the frequency change to form a feedback closed loop control. Another input will be this setting frequency. So if you move this point, which is a motor turn screw up and down, you can set up the initial position of this A, which define how much speed you can operate this rotor. So there will be a 2 input from this component, and which have both been modeled in that transfer function. So which will be one is the feedback frequency, the other will be the setup power, because everything has been considered as per unit. So the frequency, all the signal, they can be considered per unit value. This is the major part of the low frequency control. So that will close this loop and make it be a negative feedback. So it will form a droop control. The R here will indicate the slope of the droop control. The smaller R means you have better control, because this feedback signal will be multiplied by 1 over R. So if you take very small R, oh, sorry, I didn't distribute the slides. Yeah, but we haven't gone to the new slides yet. So the frequency deviation in real time will be multiplied by this gain, which is 1 over R, and translated to the power signal compared to the reference, and that will determine how much you want to change on the gate. And the gate will be translated after a time constant tau g to become a valve opening change. And after another tau t will become the mechanical power change. And compared to the load change, then it will influence the frequency deviation using the swing equation. So that's the whole idea of the frequency control. So this plot diagram is good for only small signal if we consider the frequency deviation near the equilibrium point. It's because we have ignored all the nonlinear functions or nonlinear component of the control. So in this loop, we can consider two input. One is the load change, okay, here, and there's a negative sign. Why there's a negative sign? Because we need to compare this one against the mechanical power change. So in the swing equation, the power to accelerate the rotor will be the PM minus PL, will be the mechanical power minus the load power. So PL here is like a PE in the early section. So which is power from the grid side. Another input will be this reference value. So this reference value defines how much power, how much mechanical power this generator unit is providing. So if you increase that reference value, the PM also increase. Definitely after some dynamics through some time constant. So this is just one of the transfer function. If we want to study how the frequency change with the load change, you can definitely write down another transfer function, which is how the frequency change with the change on the setting point, right? For that case, so that will be the delta omega r divided by the delta p ref. And this transfer function, the numerator will be whatever on this on the loop from the input to the output, right? And the bottom is same. Bottom is still same same equation, which is called same expression. So that is equal to 1 plus the product of everything on the loop, if it's a negative feedback. We also derive the steady state frequency due to a step change on the load, which can be estimated by this one if we consider the final steady state value of the frequency. So delta PL is the change on the load and divided by two items. One is D, the other is 1 over R. So the size of the denominator will affect how much frequency it's going to change. For instance, if there's no load frequency control, and so the only item we have is D. D is the factor from the frequency sensitive load, because D usually is very small. So without low frequency control, even very little load change will cause large frequency deviation. So this one has been confirmed by one example in the previous lecture, right? We consider only 1% of load change. The frequency can be very bad. It will be vary by maybe 0.8, almost 1 hertz. So that's why we need low frequency control by introducing this R. Because R usually will take very small value. A typical value can be 0.05. So 1 over R will be about like 50, okay? So even D can be very small from 1 to 2. So that will make denominator be like around 50. Sorry, around 20, because if R take a 0.05, 1 over R will be 20. If it take a 0.02, the denominator will be about 50. So that can largely decrease the frequency deviation and the steady state. This just shows the time response after a change on the load. First, you see the frequency will decline. So this slope, it will follow certain slope to decline. This slope depends on the inertia. Then the governor will try to recover the frequency back. And eventually there will be a steady state frequency deviation. And that frequency deviation cannot be 0 by using the governor. In order to bring that one back to 0, we have to introduce another control. The reason is the low frequency control by governor only is, this is basically just a proportional controller. Proportional controller cannot eliminate the error of the control variable. You have to introduce some control which is similar like integral controller. So does everybody know like integral controller, proportional controller, and differential controller? Yeah. So basically, proportional controller is just you measure whatever deviation, right? You want to reduce or eliminate, and measure that deviation and multiply that one value by some number. Usually that number is supposed to be large enough then compare it to the setting value. Okay, so that can help because to mitigate the error. Because if that delta omega increase, the feedback signal will be increased, right? So compared to the setup value, and the valve opening will be increased. So then it will finally influence. Will go to the opposite direction, try to do any control to decrease that deviation. But the control value is proportionally depending on the variation. So in order to make this control be functioning, the deviation has to be non-zero. So it will never eliminate the deviation. In order to get rid of the frequency deviation, you have to introduce another type of controller. So that behaves like an integral controller. Okay, integral controller will integrate the effect of the deviation and accumulatively. And finally, it can eliminate that error. So that is the idea of automatic generation control, AGC, but we will cover that one later. But now you just know we can recover the frequency back to be close to 60 Hertz, but it will never exactly go back to 60 Hertz. Another thing we notice is the frequency drop to the lowest frequency, and then you see the increase of the mechanical power actually happened later because there's a time delay or time constant from frequency deviation all the way through the mechanical power change, because there's a two time constant. One is with the governor, second with turbine. So total time will depend how soon you can influence the mechanical power. Another thing we mentioned is if there's many generators together supporting the system's load, each generator has the governor, and we can utilize this parallel circuit rule to calculate the equivalent R, and use that R value to calculate the final frequency deviation. And we raise this question whether the smaller R the better. Okay, but by the remaining time of this lecture, we'll address that question. So this is one example from Sadek's book. It gave all the typical value. So you can tell the turbine time constant is ½ second, governor time constant is 0.2 second, inertia 5 seconds, inertia time constant 5 seconds, and it asks you to design the R value. It also gave you some other information like D will be 0.8, which means 0.8% of change on load will happen if you frequency drop by 1%. It mentioned there's a number of methods you can use to design the R value, the best R value, or maybe the range of R value. One tool will be the Ross Hurwitz array or Ross table. The second will be the root locus method. So we'll quickly go through both methods. You can even use the Simulink to design the circuit or the block diagram. I'm going to share this toolbox attached with Sadek's book, so you can find this example. For each example, it gives you a file name, which is the MATLAB code. You can run MATLAB code by changing the value and do your test. Okay, so this is the transfer function. So now we just redraw the transfer function to make the input, which is a load change on the left-hand side, right? And the frequency division to be the right-hand side to make it convenient. And so there's a loop. When we close loop, that will make the control be able to function to mitigate the error. And to study the stability of this control, usually we need to first investigate the open loop transfer function. So by open loop transfer function, which is simply just multiplication of everything along the loop, ignoring this negative sign. There's a negative sign, but you don't have to multiply this negative sign. So later, this negative sign will show up in the closed loop transfer function. But right now, when you determine the open loop transfer function, you just assume there's a negative sign somewhere on the loop. Okay, then you just calculate the multiplication of everything. So here we assume this 1 over R to be K. So this will be the gain. This is some value we need to determine. And there's a forward channel, which we call it the JS. That's directly multiplication everything from the load change until the speed change. So this is basically just one equation. And this is multiplication of another component from the turbine and from the governor. Okay, so there's a time constant from turbine governor. So if you multiply everything along this loop, so this will give you the open loop transfer function. So you do some simplification, you have a denominator which is a third order polynomial, right? Numerator will be k. And characteristic equation is defined to be 1 plus open loop transfer function. Okay. So if you don't have a negative sign here, if the feedback is not negative feedback, so this sign will become negative. So usually because it's a negative feedback, so it will be 1 plus. You can easily prove. Okay. So anyway, so characteristic equation will be the denominator of a closed loop transfer function. So that's why this is very important to study stability. To solve the characteristic equation, to make this one be 0, and you can solve all the rules. So now S will be the Laplace operator, right, which is the frequency, and K will be the only unknown variable, unknown things we want to solve. So you want to solve this equation. And if this equation have all roots on the left-hand side of imaginary axis, so the system will be stable. But now, because K is unknown, so we need to find out the range of the K to change, such as the stability can be maintained. Okay, so there's a necessary and sufficient condition for stability of a linear system. All roots of the characteristic equation, which are also the poles of the closed loop transfer function, have negative real part, which means they are all in the left-hand portion of the S-plane on the imaginary axis. Then this system has to be stable. Then the next question will be how to find the range of K, such as all the roots on the left-hand side of the S-plane. The first method will be the Ross table method. So this is based on the Ross Hurwitz stability criterion. And this method can tell the sign of the roots of any like polynomial equation. So this is assumed to be our characteristic equation with all the coefficients here. The Ross table is defined in such way. So it will utilize the coefficients of each item of the equation to come up with a table. So I color those items just to make it clear. So the first two rows is very simple. Okay. So you start from like AN. If this is the first one, and that will put on the top left corner as the first number. Then the next one will be the third one, starting from the highest order. So which means this is AN, this will be AN minus 2 and AN minus 4. The next one will put it under in the second row. So AN minus 1, AN minus 3, AN minus 5. So then you depend on how many items you have, the order of the equation, you will have 2 rows already there. So then you need to come up with the third row. The third row have to be calculated based on this general formula. The general formula will be so the numerator will be different between two products, and the denominator will be one item. Okay, so the difference of two products, the first product will be from one from the first column closest to this item, which is this one. And another one from a column after this current column, which will be this one. So AN minus 1 multiplied by AN minus 4 minus another product, which is AN multiplied by AN minus 5, divided by this one. Okay. You don't have to memorize this one. If you want to use this table, you just find this slide, or maybe you print out this table and try to match this value. Okay. So how about this one? The B1. B1 will be an multiplied by n minus 1 multiplied by n minus 2. Okay, because that will be the next column. Minus n multiplied by n minus 3, right? Divided by still this one. So what if when you continue calculate until you have maybe all the element on the right column to be all 0, then you just simply put 0. If there's no such number, you just put 0. Like for instance, if the coefficient only stop at those two numbers, and everything in the dot will be 0, and you just simply put 0 on that formula. You are going to do a homework. You can practice how to use this table. Okay, once you generate this table, there's such a principle which is very useful to help judge stability. The principle says that the number of roots of the equation have positive real parts is equal to the number of times of sign change in the first column of the table. Okay, so what does that mean? So necessary and sufficient condition for stability of this linear system is equivalent to finding the first column. If every number in the first column is positive, then this system is stable. Okay, so we find the characteristic equation and generate this table, and if first column is all positive, then this system has to be stable. So we use that system as one example, right? K here is something we want to figure out for the range. So to calculate the Ross table, so this one will be here, and this 7.08 will be under 1, and then this number here and this one be here. And the K and the 0.8, because they both constant value, we just put them together as one number. Then the first item in the third row will be important. But this one will be equal to 1 multiplied by well, just let me just draw this one. Okay, so it's equal to 7.08 multiplied by 10.56 minus 1 times parentheses 0.8 plus K. Okay, so do some simplification. That will be the numerator here. The denominator will be simply this number on top of it in the first column. So this will come up with this number. And this one will be 0. Because there's no such third column. So when you calculate the item in the third row for the second column, you have to utilize the number on the third column. But there's nothing on the third column, so everything will be 0. Then that will make this one be 0. And when you calculate the fourth row, you'll still be able to calculate that 0 value, because for this item, that will be, you draw this cross. So the item on the fourth row will be equal to 0.8 plus K multiplied by this fraction. Then you just do some simplification and also divide it by that fraction. Okay, so we want the first column to be all positive, which means to make this fraction to be positive, K has to less than this value, the 73.9. To make this bottom item to be positive, and K has to be, because K is positive anyway, K is just the control gain. It has to be positive value. So that will make this one, the last item, to be positive anyway. So finally, the K has to be smaller than 73.9, which means the R has to be bigger than 0.0135. Okay. This is, maybe I only, let me let's talk about that. The next method, I would maybe need to spend more time on that root locus method. But before that, we can just verify what we get so far. So we know the R has to be bigger than 0.0135. So what if we take a value 0.05, bigger than that stability boundary? So we'll have this closed loop transfer function. And for this closed loop transfer function, if we make S to be 0, so you can actually calculate the steady state frequency. Okay, so if you translate this steady state frequency back to hertz by multiplying that per unit value at 60, which means if you take a 0.05, which is bigger than the stability limit, you'll have frequency deviation like this one. The deviation is 0.576 hertz. Okay, it's better, right? But it seems not to be not very normal, because we expect to have a less than half hertz deviation. So what if you earlier we said if we don't have low frequency control, which means R will take infinite. So if R take infinite, this part will be 0. And the load change will completely add it to the sensitive load. And finally, the frequency deviation can be, for this case, can be 15 hertz if no low frequency control. So if you divide the load change by only D, okay, that will give you very large frequency deviation. Another thing is, what if we have a even,
We are 7 minutes over.
oh, sorry. Yeah, we can stop here if you want. Let's continue. So the last slide just show if we take the boundary value, the system will be marginally stable. Okay, although the frequency deviation is still not back to 0. All right. Okay, so I will see you on Thursday.